let's begin. So I think we had some examples to finish up last time from 6.3, 6.4. Where we start? Did we do any of the integration examples? No, right? So it's integral of pi over x dx, integral of 1 over 2x dx, integral of 1 over x squared dx, integral of cotangent x dx, integral of radical x, radical x. Okay, so you guys had a couple days to think about this. What do you guys think about the first one? Yeah?
Pi is a constant, so you could pull that out front if you wanted to, and that's just 1 over x, which we know.
So what is that?
Absolute value of x.
Absolute value of x plus c. And yes, technically this is in parentheses, the pi multiplies the c, but I'm just writing that as another generic c. B. What happens?
You can do the same thing as what the one.
Right. So 1/2 you can pull out. Be exactly the same thing. What's that?
Maybe 1 over x.
Okay. I wanted to see if anyone would think that this is ln of x squared. It is not. You would write it like that, and then do the power rule. It's only ln if it's linear in the denominator. D. How would you do? Figure out the integral of cotangent. Hmm?
Cosine ln absolute value of sine x.
How do you get that?
I made cotangent cosine x over sine x,
Cosine x over sine x.
and then u was sine x. Does that make sense?
So then you said u equals sine
Yeah, and then du. Oh, wait, what's
over cosine x dx, right?
this? Yeah.
Which is that part. So this means your integral would become
Oh,
1 over u du, which is?
Ln absolute value u du plus u.
So then it just becomes ln of
Sine.
sine x.
Do you divide by cosine? Or?
Do I divide that?
I just don't know where the cosine would go. 'Cause
Well, it went into the du.
oh.
Right, du is cosine dx, so when I see this cosine dx,
Uh-huh.
that's du.
Okay, yeah.
We could have done it, in class we were doing this whole thing where we were like, okay, when you had that du cosine x dx, you solve for dx to be du over cosine x. But in that case, you'd have that cosine x, you'd have the u, and then you'd have du over cosine x, and then it canceled there anyway. So there are a couple ways you could do it, but I just saw it was right here, so I just swapped it out. Ideas for this one?
Set u equals to the square root of x.
Du would be?
So 1 over, d will be 1 over square root of x.
1 over 2 radical
Oh,
x.
sure.
Yeah?
Okay, yeah.
So you can solve for the dx. That would be 2 radical x du. And so now you go and you kind of swap those out. So now we have 2 over radical x. I'd leave that one because I'm going to want it to cancel with this guy. And I change this radical to the u. And so now my dx becomes 2 radical x du. Now the radical x is cancelled. 2 times 2 is 4. So you have that. And what's that? ln of e to the u? Right? It's 1 over e to the u. No one objects. Yes?
So since the square roots of x cancel.
Well, that's not what it is.
Oh, it's not?
No. I wanted someone to object. How do you integrate 1 over e to the u?
Natural log e to the u?
No, I just said that's not the answer.
Oh, wait. No, never mind.
Make it be the negative u.
And what's the integral of e to the negative u?
-1 e to the negative u. Or 4 times -1.
Yes, but only because it's equivalent. Technically you're dividing by the -1, so don't forget that rule. Remember what the rule for e to the kx dx is 1 over k e to the kx. So technically you're dividing by the -1, but yes, it's equivalent to multiplying by the -1, so this becomes -4 e to the minus u. That becomes -4 e to the minus, our u is radical x. Let's see. So I didn't catch you guys with this one, but I caught you guys with this one. Right? It's very important that you know it's not 1 over something is not automatically ln. That you don't want to have that in your head. It's when you have 1 over a linear function that you get ln. Because all these other rules, we can rewrite them and apply rules we had before. Right? The only thing that was missing was, like I said, when n was equal to 1 in the power rule, that's where ln comes in and helps us. But otherwise, we can just use previous rules that we had. So be careful of that. That I actually listed this in the syllabus, so at this point you'll probably understand what I'm talking about. When I said, don't make the mistake of thinking that 1 over anything, the integral of that is just ln of the thing. It's not true.
Wait,
Yes.
where did you get the -4 from?
because the integral of e to the negative u du is minus e to the negative u. And that minus, I just moved it out in front. So technically it's 1 over minus 1, so you can write that as just minus. Right, multiply top and bottom by minus 1, we get the minus 1 in the top. Okay. F. So be careful with the rules. Don't have that knee-jerk reaction. If 1 over something is ln, it's not always true. Okay? Yes?
Sorry, just to clarify, so the only time you get ln is if it's a linear function with a single variable power of x?
Yes. So if you have something like this, ax plus b, and you're integrating that, you can use the substitution, and you would have this. It's very rarely where 1 over something would give you ln otherwise. I can't think of a case where that would happen.
Okay.
Right, but yeah, to get an ln from an integral, it has to be 1 over a linear function. Because that's the guy where the n was minus 1 that we couldn't deal with before. Otherwise, if it's a square or something, it means you have to do something else. It's not going to be an ln.
Okay.
And you again, you can always check. Let's say it, and this is another level of your understanding. Let's say you incorrectly believe that this was equal to ln of e to the minus. Let's say you believe that this was e to the u. But what is this? That would actually just be equal to u itself. And I know that if I differentiate u, I'm not going to get that, right? So it really doesn't even make sense. Once you make that mistake and have an answer, the answer is not going to make sense. But you can check for yourself. If you differentiate this, you will get that. Okay, draw this one. Yeah.
Substitute u in for 1 plus e to the x.
So du is equal to
E to the x.
e to the x dx. So if you'd like, you can solve for the dx. But I mean, I see the e to the x dx right here, but if you're partial to doing it this way, you can do that. So here you have e to the x over u times du over e to the x. The e to the x is cancelled. That just becomes 1 over u du. That's a linear function, so that becomes ln of u. So this becomes ln of 1 plus e to the x plus c. Now technically speaking, this is always positive, so you don't need the absolute values, but there's no harm in leaving them there. So just always be safe and just put in absolute values. But this is always positive, so the absolute value is actually equal to the same thing. So if, for example, in your textbook they don't put absolute values, don't be confused as to the rule is wrong. It's not the rule is wrong, it's just that the absolute value of something that's positive happens to be itself. But leave it there. And if you follow the rules of ln and differentiate that, you realize you'll get that. You get u prime over u, you do this. Where are we now? This one. G. Yeah.
Let u be x squared plus 4.
X squared plus 4. So your du would be 2x dx.
And divide both sides by 2x.
d over 2x would be dx. You go here, have x over u times dx, which is du over 2x. The x's can cancel. You can
Take that
factor out
out.
that 2. That becomes ln. And then it's 1/2 ln of x squared plus 4. Technically absolute values aren't necessary, but leave them. It's not wrong to have them. Yeah.
Alright, sorry, I'm still harping on this, but, in both those, like, the denominator wasn't linear function, so how do you,
Yeah, but the top wasn't a 1 either.
oh,
When I rewrite it so that it looks like 1 over something, and then I want to apply the ln rule to that, right? 1 over something, that something has to be linear in order for this to happen. That doesn't even apply here. I'm nowhere near having 1 over something. There's an x on top.
okay, so like if you got it in the form of du over u,
Yeah,
okay,
but this doesn't have that form.
okay, okay.
I'm just talking about, a lot of students think that when they see 1 over anything, it just becomes ln of that thing. That is incorrect. That is not true. Right, this thing has to be linear in order to get an ln. Okay. Now, if something's presented to you, clearly it's a division, but it doesn't look like 1 over anything in the first place, so you wouldn't, I don't think you would think of that rule. But once you do a substitution, you get to a point where you have 1 over something, you have to make sure that in order to get an ln, that's actually a linear thing. It didn't have to be that way, right? Because I could show you a small, slight variation on the same integral. If I had x divided by x squared plus 4, and that was squared, now that's a different story. That's no longer going to give you an ln. Right, because now if you do the u equals x squared plus 4, your du is equal to 2x dx. So then you're going to plug this in. This is going to become 1/2 1 over u squared du. And it's not an ln anymore. Right? Because once you write it in the form of 1 over something, that thing is not linear. So this would be minus 1 over 2, 1 over u. So that would be minus 1 over 2. Right? So that's what I mean. Once you can write in the form of 1 over something, you need to make sure, don't just have a knee-jerk reaction of going into ln, because it's not always ln. It's only ln if it's linear. So just that one little variation on this problem completely changes the answer from an ln to a non-ln. So it's something you do have to be careful about. Right, and make that a 1/2 power x over the radical of x squared plus 4, and the answer will look very different again. So you just have to be really careful and make sure that you're applying the rules exactly as stated. Right, if something doesn't say it can be any power you want, don't assume it's any power you want. It's only the first power. Okay. Do a little bit of fundamental theorem of calculus here. Okay, what do you guys think? Yeah?
Make u equal to ln of x,
U equals ln of x.
and then
du,
du equals 1 over x dx.
derivative of ln x is 1 over x.
And then x du equals dx. And then the x's cancel out, and you have 1 over u du.
So we had 1 over x times u times x du. The x's would cancel out. What about the limits?
Oh, we'll plug the limits into,
One.
Okay, so there are two ways you can
1
deal
over
with the
x.
limits.
or ln x.
Let's actually look at those two ways. So here's something. One, you could leave the limits alone, that's possible, but you need to remember that those limits are in terms of x, not in terms of u. So to remind yourself of that, you can write here, x equals 2. X equals e. All right, just to remind yourself that q, that I should not be plugging that into u because it's an x value. All right, so that's one thing you could have done. So that would have been the step that you could do here. So you can think of this as x equals e up to 2, 2 up to e. X equals 2 to e of 1 over u du. So that you would integrate, you get ln of u, where x goes from 2 to e. Right? And then what you can do is, because you know you have to plug in an x value, you have to rewrite this first. So then you go here, and that was ln of ln. And now you can plug in 2 and e. And so you plug in ln of ln e minus ln of ln 2. What's ln of ln e?
0.
It's 0. And so this is 0. And so minus ln of that's your answer. So this process here, this is called back substituting. Okay. That's when instead of u, you plug in the formula that you originally made u equal to. Another option you could have done is you could actually change the limits. Right? To do this, you use the substitution equation. Right? So we have u was equal to ln x. This means when x is 2, your u should be ln of 2. And when x is e, your u should be ln of e, which is 1. And so then you could rewrite this integral as the e you would change to 1, and then the 2 you would change to ln 2. And that's 1 over u du. And then you could do this guy, ln of u, and then you plug in 1 and ln 2 into that guy. So you have ln 1 minus ln of ln 2. And again, this goes to 0. So you get minus ln 2 of ln 2. So there are two options. You can leave the old limits, back substitute, make sure that don't plug these numbers into u because they refer to x, so you have to replace the u with the function of x, and then plug in the limits. Or you can actually change the limits, and then you don't have to back substitute, you plug them directly into the u. That being said, I do have a recommendation about that. See, the back substitution process can actually be very annoying. Later on, we're going to cover something called trig substitution as a technique of doing integrals. And the back substitution process, when you're doing a method like that, is actually pretty time consuming. So I would probably recommend the following. Sometimes back substitution is annoying. So it is better to change limits. Highly recommend that you change limits. When doing a definite integral. With trig substitution. We'll look at that in the next chapter, but there are other methods where this is annoying, but in calculus 2, I think this is the only method where it's particularly annoying. You could just take the rule that you always change the limits and then you don't have to worry about this, but otherwise it's optional. Do what your preference is. But yeah, there are cases where it's much easier for you to just change the limits and use the new limits instead of the old one. And when we get to trig substitution, you'll see what I mean. Because trig substitution involves it's kind of like a substitution, but you change the variable in such a way that you introduce the variable theta and trig functions, and to actually go from the variable theta back to the variable x, you have to like set up triangles and use SOHCAHTOA and all sorts of stuff. And use trig identities and things like that. So it can become quite annoying. And so it's much easier to just plug into the little trig equation that you have up here and change the limits. Let's do that. That looks pretty scary. But is it scary? Yeah?
Let u be x cubed plus x.
Okay. U equals x cubed plus x.
Take the derivative.
Let it be ln u x cubed plus x.
Why won't this work? Let's actually follow this. Let's follow this road and see where we end up. What do we do now? What would you do next?
Multiply du by 2 to get
Sure, 2 du would be that 6x squared plus 2 dx. Yeah, and?
plug it in du pi. I don't know how it's gonna work out.
Okay, so this guy would be replaced just by 2 du, right? The denominator we replace with u. In the numerator, you replace with pi to the ln of u. How do you deal with this one?
What's the one more complicated?
Well, it does look more complicated than that, for sure, because this one had something multiplying, this one didn't. But how would you deal with that? Here's what you could do. Realize that this is 1 over u times pi to the ln, right?
Yeah.
So one option, if you did this, was do another substitution, right? Because the derivative of ln u is actually 1 over u. But to me, that's overkill. Like, I wouldn't do it that way. There is a better substitution to use. And someone suggested we take the ln into account. So I want to do that, and we'll talk about why we might think to do something like that. So let's, yeah, and what would this be?
3x squared plus 1 over x cubed plus x.
We could again do that whole multiplying by 2 thing. And now what you notice is that this whole thing here gets taken out.
Oh. That makes it a lot more easy.
So now we would just end up with 2 du replaces that whole thing. Our u is actually the ln, so that just becomes pi to the u. So, and how do we integrate something like that? Pi to the u du. to integrate pi to the u. What rule would you use? What kind of looks like pi to the u? Yeah?
Would it be pi to the u over ln of pi?
There's a rule that says the integral of a to the u du is a to the u divided by ln of a. And your a is just a constant, pi is a constant, so that rule applies. So this is just going to be 2 pi to the u divided by ln of pi. And now I substitute what my u is. So this is going to be 2 pi to the sorry. So this is going to be 2 pi to the ln of x cubed plus x over ln pi plus c. So I never really covered substitution with you guys, so you might not, we never really spoke about it. But remember the point of a substitution is that you have these basic rules that you have, right? You know, you have rules like this and x to the n and how to integrate all these functions. The goal of when you're doing a substitution is to make it look as much as a basic rule as possible. We don't have a basic rule where there's an ln in the power, so I would want to get rid of that. Having the ln looking here and seeing in the power that there's an ln, to me that's the most complicated part of this function, and that's the guy I'd want to get rid of. Okay? So remember your u that you're substituting, you want to substitute a part of the function that makes it simpler. Simpler means it fits on top of a template for a rule that I have. And because in all the rules that we have, our powers are single variables, that guy is insanely complicated. So I try to make that my u, and hopefully when you do the derivatives, things work out, because in order for substitution to work out, once you differentiate the u, its derivative should be somewhere else in the function. Okay? Now, in the event that you can do that, make a substitution to get rid of the complicated part, but its derivative is not somewhere else in the function, then you need, substitution just wouldn't work. You need another technique. We'll learn techniques to deal with that later. But yeah, we're now officially in the realm of me being able to give you these integrals that look extremely nasty, but they're really nice in disguise. And then we'll get to the integrals that both look nasty and are actually nasty. So that was the last example for this section. So the homeworks for 6.3 and 6.4 are due on Tuesday. That's February 6th, I think.
Yeah.
And we're going to move on to the next topic, which there are a lot of word problems. These usually come with word problems, so I gave you guys a handout last time, so I want you guys to look for that. You probably won't get to the examples, but I can probably talk a little bit about theory. That was actually, did I skip a section now? So this is 6.5, exponential growth and decay. can look at a definition. Quantity is said to grow exponentially if its rate of growth is proportional to its current size. And you could also say something like decay exponentially if its rate of decay is proportional to its current size. Okay. The difference is growth is of course means increase, decay means decrease. Yes.
On the top is proportional to its current size?
To its current size,
Oh,
yes.
it looks like an O almost.
Oh, sorry. CU, that's a U. CU current. Okay. Now, because growth means increase in size, if you're describing a rate, right, like a rate of change, what sign do you expect it to have? Positive. So this means it will have a positive rate. This means it will have a negative rate. So those are two ideas. The formulas are going to be very similar, except when one the rate is positive, the other the rate is negative. So that's going to be important. So when you're reading a question, depending on what you're talking about, you would know to set up the equation that has a positive rate or a negative rate. So if we're talking about population and it's growing, it's going to be this. If we're talking about some radioactive substance and it's decreasing, we're going to be using this kind of thing. But the two setups are very similar. The difference is just one has a positive sign, one has a negative sign, and there are some consequences of this. But in terms of the generic general formulas, they don't have that big of a consequence. So let's actually talk about it. So let's look at growth, exponential growth. A similar treatment you can use for decay, but let's just talk about growth for now. By the definition, let P of t equals the amount of this quantity at time t. In other words, that's its current amount. Right? P of t is a function that measures the current amount of a substance or a quantity that I care about. This means that its rate of change is proportional to its current size. Right? Proportional means just a constant times it. This r is r here is a constant. Right? And it will give you it's called the growth constant. And you can think of it as describing the percentage change. So that's kind of the rate at which something is growing. Such an equation is called a differential equation. There's an entire class on differential equations. But we're going to just be doing like a couple of them here. This is just an equation with a derivative in it. Right, so you have a prime being a part of an equation, you call that a differential equation. Sometimes we don't want to have differential equations. We want to get rid of a rate and describe this quantity in terms of some other generic variable. Now, one way we can do that is the following. Given P prime equals RP, we can actually write this out as dP dt equals RP. So I'm writing the Newton's prime notation in Leibniz's notation. And Leibniz's notation is very, it's a nice notation because it's very versatile and it kind of can do what you think it can do in terms of how it looks. It's a fraction and you can kind of treat it like a fraction. So one thing you can do is you can multiply both sides by dt, believe it or not. And I want to get all the p's on one side and all the other guys on the other side. So I can divide both sides by p. Assuming I have a non-zero quantity. And then what I can do is I can throw integrals in. And now notice that I have something that's in the standard looking way of an integral. What's the integral of 1 over p?
Natural of p.
An integral of r with respect to t? RT plus c. Right? And now what I can do is I can solve this equation for p, which is what I care about. I care about the quantity, right? Finding its current amount. So I can raise both sides with e, right? The rules says that would cancel out, get p here. This would give me e to the RT plus c. I can rewrite that in a little nicer form here as well. I can write this as e to the c times e to the RT. By realizing that when you're adding the powers, this means you're multiplying things of the same base. This c here, I can call it a constant e to the RT. So okay, p equals c e to the RT. So a quantity that obeys this rule can be described as an exponential function. And that's why it's called exponential growth. If you describe a quantity that grows like this, it's actually exponential. Now, how do we find that c? Right? So now, suppose p of 0, meaning the amount at time 0, is going to be p little naught. It's a notation. Then what I can do is say when t equals 0, I know my p is equal to c e to the r times 0. This means my p of 0 equals to c. That just means p naught equals to c. Therefore, I end up with this formula. P is equal to p naught e to the RT. Yes?
So if you raise natural log absolute value p to the e, the answer, you can take off the absolute value.
You can actually do the whole thing where you branch it off and write it as positive p and negative p, and it'll all work out. It'll also be the case that because you have this c in front, if the p should be negative, when you're plugging in the values that you're given, this will end up being a negative number. So it'll all work out. It's not something you have to worry about.
Okay.
But yes, well, you should worry about it, but I'm saying you now that you don't have to worry about it. Okay? And that's a general formula for something that grows exponentially, right? Without any external factors affecting it. If it's just left alone to grow, that's what it would look like if it's growing proportional to its current size. I call this the Pert Formula, P-E-R-T, like the shampoo. I don't know if you guys remember that. You're probably too young to remember that, but yeah, Pert was a big thing when I was little. It's like the first time, what, shampoo and conditioner in one? That's amazing. That's so convenient. I'm gonna save so much time. Anyway, yeah. So we'll stop there because I think we're out of time, and we'll talk a little bit more about these forms and how we can derive some of the other things, and then do the work problems on Tuesday. So on Tuesday, you have a quiz on everything we did this week. Wednesday.
Okay.
I don't think
Mine's right now.
I also posted it on my